Yeah. Hi everyone. Firstly, I want to thank the organizer for this opportunity to give a talk this workshop. Today, I will talk about the Caen-Jacobi identity and its applications in graph theory. So, in this talk, I want to present a new application of the so-called Caen-Jacobi identity. This was first studied by Caen in 1998. He used the identity to solve problems in strongly regular graphs. So we read this during our study. We rediscover this identity and we rename it as the Caen-Jacobi identity. 2018, Dr. Gary Griffiths considered the following graph: the regular graph on 60 vertices with valency 22. Has these four eigenvalues. The existence problem of this graph is quite challenging because spectral is quite close to be a strongly regular graph. So it has four eigenvalues and the multiplicity of -8 is quite low here. So recently, in a paper of me and Dr. Griffiths, we managed to apply this identity to show that this graph does not exist. And furthermore, this also, in fact, this implies that there does not exist 60 equiangular lines in R18. So not just that this graph does not exist, it further implies that the maximum number of equiangular lines in R18 is at most 59. So as you already see last week during the mini course, Dr. Griff introduced these real equiangular lines. So real equiangular lines is a set of lines through the origin in RD such that the angle between any pair of lines is constant. And a particular interesting problem is to compute this ND, which is the maximum number of equiangular lines in RD. So in our paper, we combine this identity to show that gamma does not exist. And also we include our recent papers where we systematically rule out possible candidate characteristic polynomial for Seidel matrices, as you see also in the mini course last week. So together we managed to show that if gamma does not exist, then N18 is at most 59. So this is a new upper bound for N18. Given a square matrix M, we use this convention. The characteristic polynomial is simply the determinant of xi minus m. This Caen-Jacobi is as follows. So given a graph G and adjacency matrix A, let phi G be the vertex set. So first we take a subset T of the vertex set, and then we define the T bar to be the complement. And if AT denotes the principal submatrix with rows from T and columns from T, then the identity gives a way to compute the characteristic polynomial of the complementary subgraph. So this AT bar, we call it a complementary subgraph of A with respect to T. So it's equal to the characteristic polynomial of A multiplied by this expression here. So it's equal to the determinant of this matrix. So first we have to take the inverse of xi minus A, and then we take the principal submatrix, and lastly we take the determinant. So this this factor here is the tricky part of this identity. Yeah, and also this graph, this identity doesn't just hold for special case of like adjacency matrix of graph. It actually holds for bigger family of matrices. So in his paper, they can simply state it as Jacobi identity. And I think we decide that it's appropriate to rename it as the Caen-Jacobi, especially since it seems like Caen is the first one to apply this identity to problems in graph theory. So that's why we just rename the identity as for this particular problem. Of a small example, so let's say we take a Peterson graph. We have this vertex set 1 to 10. I take T to be 1 to 5, 6. So this induced subgraph is isomorphic to K13, also known as the claw graph. And then the T bar is 3, 4, 7, 8, 9, 10. Using the identity, we can find the characteristic polynomial of the A T bar. We note that the characteristic polynomial of A is equal to this polynomial, x minus 3 times x minus 1 to the 5 times x plus 2 to the 4. So it's a, as we already know, Peterson graph is a strong regular graph. And we compute this matrix here. So it's the crucial part of the identity. We have this xi minus A inverse. And then you take the principal submatrix. So it's equal to 1 over mx multiplied by this 4 by 4, where mx is the minimal polynomial. So later we will see we find an expression to for this xi minus A inverse, and yeah, there's reason why we have this mx here. And now we just multiply those two polynomials, and then it is equal to the characteristic polynomial of the complementary subgraph. In this case, it's isomorphic to the cycle on 6 vertices. Interestingly, this identity can actually be derived from properties of Schur complement. So Schur complement is a very established theory developed in linear algebra. So recall that we have this M, and then we have square matrices P and S, and all entries, let's say, is from a field K. So if P is invertible over K, then the Schur complement of P is defined to be this M slash P is equal to S minus RP inverse Q. So we want to apply the properties of Schur complement to derive the Caen-Jacobi identity. The first important property is that the determinant of M is equal to the product of determinant of P and the determinant of its Schur complement. And the next property, so suppose we set M to be xi minus A and P is set to be M T bar, which is equal to xi minus A T bar, then we will have M inverse T is equal to the inverse of the Schur complement of M. So this interesting property allow us to derive the identity. We take the determinant first, and then you have determinant of the Schur complement multiplied by determinant of this M inverse T is equal to 1. Then multiply both sides by determinant of P. Yeah, that's where we can get our identity. So the main topic of today's talk is about how we find a new application of this identity to show that there does not exist a regular graph gamma with the following characteristic polynomial. Okay, so first, suppose such graph exists, and then we introduce some notation here. So we take this TU to be subsets of the vertex set P gamma, and then we use the following notation. So gamma T is just the induced subgraph of gamma on T. And then AT comma U is the submatrix of A, where the rows are from T and then the columns from U. And finally, AT is just the principal submatrix, or it's the same as AT comma T. So yeah, particularly the second one is probably uncommon, this AT comma U. So we'll have to use this for our talk. As mentioned before, gamma is close to be a strongly regular graph, and in fact, you can find a partition omega of this vertex set of gamma. into 3 blocks or 3 parts of equal size. So each part has size 20. And suppose that we rearrange A, or we position the entries such that this block matrix, right, in the diagonal, we simply have the adjacency matrix for each partition, for each part of the omega. And it turns out that it's this graph gamma satisfy this following equation: a squared plus 4a minus 12i, I is the identity, is equal to 9j60. Oh, so
It's in the building, just ignore it.
any question?
Yeah. It's somewhere along the lines.
Yeah, it's in like the calendar. Or longer near my building. Or somebody knocked into this.
So maybe let's go.
I cannot hear the question.
I don't think there's a question actually.
Oh, yeah.
Everyone, can you please mute your microphones so that there's no interruption? Thank you very much.
So this adjacency matrix satisfy the following equation. So the right hand side we have 9j60 plus this Kronecker product of I3 and J20. So the J is the all-one matrix, and as we see here, this part here, the I3 Kronecker J20 is what separates this graph to be a strongly regular graph. So if we don't have this part here, then it's just the very common formula for that we usually encounter for strongly regular graphs. Furthermore, this partition is also equitable. So it has this following quotient matrix. So any vertex in T1 will have, it must be adjacent to 2 vertices in T1. Any vertex in T2 is adjacent to precisely 10 vertices in T1, and so on. So as a consequence, we see that if T is from omega, then gamma T must be a disjoint union of cycles, and any vertex outside of T is adjacent to exactly 10 vertices in T. So far, we managed to find the structure of the graph by looking at the eigenspace. After that, we need to use this identity to gain more information. Here we have a lemma to help us compute what is the inverse of this xi minus a. So we let this linear operator D defined to be, so it we take D of xi equal to xi minus 1 for I positive, and D of x to the power 0 is just 0. So it's similar to taking derivatives, but simply reduce the power and then remove the constant. So this is how we define the linear operator. And then the lemma says that the xi minus a inverse is equal to, we have this 1 over mx multiplied by this sum here. Mx is the minimal polynomial of a. And then a small example. So we take M to be this 3 by 3 matrix, integer matrix. The minimal polynomial is equal to x squared minus 11x plus 10. Then we have this D1 is equal to x minus 11, and then D2 is equal to 1. And if you keep taking the D cube and so on, you simply get 0. Then applying the lemma, we have that inverse of xi minus m is equal to x minus 11i plus m over this mx. Back to gamma, we have this A as the adjacency matrix of gamma, and then again we arrange the entries such that this block matrix have AII is equal to the adjacency matrix of TI for all I. And then the minimal polynomial is equal to x minus 22 times x minus 2 times x plus 6 times x plus 8. And this equation is what we have seen before just now. So we combine this with the formula for this inverse. So we obtain that mx multiplied by x I minus a inverse is equal to this right hand side. Notice that we have 4 matrices here. So we have A, we have I60 identity, and then all ones matrix. And then we also still have this Kronecker product, I3 Kronecker J20. So yeah, it's quite important that we have this A here. It instead of like higher power of A, like A squared, A cubed. So if you only have A here, is the computation can be done. So for strongly regular graph, if you look at the paper by Caen, he also have a derived expression, something like this for the inverse, but without the Kronecker product. And yeah, using our lemma, we show a generalization of this formula. And then if you compare A and this Kronecker product, right? So you have in the Kronecker product, you have these diagonal entries of block matrices, all ones of order 20, matches with the diagonal of A, diagonal of block matrix of A. Now, let's say we take TU to be two distinct elements of the partition. So we take two blocks, block T1 or any two of the three blocks. And then let S be a subset of U. Now we observe that this, once you take this principal submatrix now, so A becomes A T union S, and then I becomes I60, just is still identity, but the size is reduced to 20 plus the size of S. Same thing for J, but for the I3 Kronecker J20, we have slightly different formula. We have J20 direct sum with J of size S. So you still have this 0 at the off diagonal. So yeah, so this part is also quite the tricky part for this graph. And unlike the strongly regular graph, if you take any two induced subgraph which is isomorphic, their complementary subgraph must be cospectral, but it's not always the case for this type of graph, especially because you have this direct sum. But for our method, we don't have we managed to overcome this. So I will show you in a few slides. So first, we obtain our first subgraph condition. The important part is that the characteristic polynomial of the complementary subgraph must be an integer polynomial, because it's just an integer matrix. And by the identity, this characteristic polynomial is equal to this product. The characteristic polynomial of A multiplied by the determinant of x I minus A inverse T union S. And after some calculations, we conclude that the determinant of this sum of matrices must be equal to this type of rational function or rational polynomial. And yeah, so this is our first subgraph condition. And if we take S to be empty set, then the implication is that the gamma T must be the disjoint union of at least 5 cycles. And if you take S to be a singleton, just take any vertex U not in the T, then each cycle must be even. So yeah, I skip quite a lot of details here, but using this, we can conclude that the graph on T, the induced subgraph, must be disjoint union of 5 C4. So yeah, it's when we do the computations, we consider all possible disjoint union of cycles. It's possible to just do it computationally, but more interestingly, using our subgraph condition, we can also deduce the same thing in a more theoretical way without any computation at all. So yeah, we're quite amazed by this. Is quite surprising. So the next step, so it means that for each block, right, you have 3 blocks in the partition omega. Each one of them must be 5C4. So what we do next is we try to grow this graph with the restriction that we already have. So what we consider is we consider graphs by adding an independent set. So you fix a block and then you add more and more vertices to this subgraph. And in particular, we choose independent set so that we will have a block of 0 matrices in the diagonal. So it will allow us to compute it more efficiently. So this is our second subgraph condition. So this is already assuming that gamma t, the graph on t, is already 5C4. So we use that, and then together with the Caen-Jacobi identity, we use the similar idea to the previous condition. We obtain that this determinant over here, so B is defined to be, so you look at the submatrix A T comma T union S, and then the AT is the adjacency matrix of the 5C4. And then you look at the vectors that form these columns of B. So the determinant of this sum of matrices is also equal, it must be equal to some rational function. So this so these two are the necessary algebraic conditions for subgraph to be an induced subgraph of gamma. So first we start from 20, and then we want to add, first we add one vertex u, let's say u, and u must be adjacent to exactly 10 vertices in T. So for any vector, we define this vector u is equal to at comma u. So it's simply this row vector besides the first block of the 5C4. And then you have 0 entries at the bottom right. So we consider this matrix as our x, as x and b, right? So the b is just this u here. B is just the u, vector u. And if the subgraph condition 2 holds, this AT union U is always isomorphic to a one graph. So we consider all possible is like 20 choose 10. Apply the subgraph condition 2. It turns out that there's only one possibility for the 21 vertex, which is in the next slide. So yeah, this is the only possibility for the 21 vertex graph. So let's say the center vertex is U. Then 3 of them must be adjacent to U in the neighboring vertices, and then 2 of them adjacent to U in the opposite vertices. So yeah, when we first find this, yeah, it's quite a nice graph. Unfortunately, it doesn't exist. Now we fix a vertex U from outside the block T, and instead of adding 1, we now add 2. So we have added independent set of size. So we take that vertex to be V, and then V must be non-adjacent to U, but they belong to the same block in U. So we have block T first. We take the block U, and then take 2 non-adjacent vertices in block U. Can we consider this vector V to be AT comma V? And now we have if you look at the matrix here, we have block of 2 by 2 0 matrix. This is allow us to apply the second subgraph condition. Now if we look at this matrix now, if we take V to be the vertex of compatibility graph, so we define this compatibility graph GU. So V is a vertex if, after looking at this matrix, the second subgraph condition still holds. So we collect all this vector V such that the second subgraph condition still holds. And it's automatically implied that the V cannot be U. So U is not in the vertex set of this GU. So we simply fix U and then we look at other vertices that is satisfying the second subgraph condition. And at the end we have there are 454 vertices for GU. And in fact, also a bit surprisingly, without computation we can also derive all possibility for these vertices like theoretically without any computation, but it's much more tedious than a previous lemma. So I think in the paper we simply state that by computation we can generate all these 454 vertices. So we have all these vertices. We define the adjacency of the graph as follows. So you take two vector as the vertices V and W in GU, and we look at this matrix AT union VW without the U, without the fixed vertex U. So again, we have this block matrix, and if the subgraph condition, the second subgraph condition still holds, then V and W must be adjacent in GU. So these two vertices are adjacent if this second subgraph condition still holds. And also an important point is, even though we fix U, right? If you change any U, take any U star, for example, other vertex, then the compatibility graph are always isomorphic. Yeah, so in our paper, we detail how we show this, that it doesn't matter what is the choice of the U that you fix. All these graph on 454 vertices, they are always isomorphic. Finally, last step. So as we see before, we have gamma T and gamma U. They are all must be 5C4. So it implies that there exists a subset of independent set of size 10, including the U. So you simply take the opposite vertices of the square 5 times, then you get independent set of size 10. You can imagine, like, in this, if you keep growing, you will have like a 10 by 10 matrix of 0 entries. So that's what we try to obtain when we try to grow this AT. However, so this subset, this 10 independent set of size 10, right, it corresponds to a clique of order 9 in the compatibility graph, because the U is already, you already consider the U, and then the rest is simply the clique of order 9 in this compatibility graph. But however, compute that the clique number of GU is only 7. So at most you can only get an independent set of size 8 in block U. So it's impossible that you can have this independent set of size 10, which is the contradiction that we want. So, and therefore we conclude that this graph gamma cannot exist. So we find a new application of this so-called Caen-Jacobi identity, and using our previous techniques, we combine it with our method of ruling out possibilities for Seidel characteristic polynomial. We managed to find a new upper bound for the maximum equiangular lines in dimension 18. So we now have N18 is at most 59, and the lower bound is 57. So still open what is the value of N18. Recently, we also have found the construction of 57 lines. So it's either 57, 58, or 59. So between those three values. And for more details, you can refer to our recent article on arXiv. So yeah, I think that's the end of my talk today. Thank you for your attention. So yeah, feel free to ask if you have any questions.
Nice talk, Jeven. Any questions from the audience?
You can double up there. Yeah, thank you for the talk. What's the next dimension that you are going to be trying to chip away at from the list of the not yet resolved dimensions of maximal equiangular lines?
I thought he would stick with 18, 58, 59 vertices.
No, but I mean, maybe the next step isn't dimension 18, but to move it to a different dimension. Like, what do you think this particular identity, where do you think it could be used next?
Yeah, I think currently the only unknown is the dimension 18, 19, 20. So only these three left, such that like you have all the values up to D41. And for this particular identity, currently we haven't found a particular characteristic polynomial that seems to require this. So at this point, so far is the new application is on this graph gamma, but we aim to apply this not just in relation to equiangular lines, but maybe for some more families of graphs, like yeah, in general, maybe small regular graph for eigenvalues. But for the equiangular lines in other dimensions, so far we have not found any possible candidates to apply this identity.
So my question is closely related. When you get to 59 vertices, how many candidate characteristic polynomials are there? Does it just grow up exponentially, or is there a small list that you can attack?
Oh yeah, thanks. Good question. So we have this lemma that to like list all possible candidate polynomials. But it seems like for the number for 59 is too many at this point. It's like I think it's at least 200 or something. I don't remember. So it's a bit
200 projects of this size is a lot of work.
yes.
Yeah.
So at this point, either we need a more stronger restriction on the characteristic polynomial, or a more efficient way to eliminate the candidate polynomial.
Thank you.
Okay, thanks.
Yes, you have a question?
This is not a comment on the mathematics, this is on the history. Actually, Dom de Caen first used Jacobi's identity to settle a problem that came up with some work that I done for other people on covers. But the first place he was by no means the first. So I think in 1977, Tut had a paper, All the King's Horses, where he proved that if the carriage problem of a graph was irreducible, then the graph was reconstructible, and he used Jacobi's identity in that. So, and the theoretical chemists were using Jacobi's identity to do questions on so-called helical molecular orbital theory, which is basically eigenvector graphs. That's in the 30s. And a final comment, it's not a very good idea to rename a standard identity just because someone's used it for a particular purpose.
Yeah.
Okay, thank you.
Yeah, thanks for the information. Yes. So yeah, I think when we find this is, so we look at the survey, I think it's by Brouwer, and then he referenced this paper in the survey, and then yeah, it's exactly what we want. Yeah, maybe I think yeah, we probably shouldn't rename it. So yeah, thanks for the suggestion.
Any other questions? If not, then let's thank our speaker again.